and we should think of space-time as being the average quantities of all these microscopic degrees of freedom. If that's the case, these things won't tell you much because it's just equilibrium statements are the important one. But if there are kind of single shot or if the fluctuations are important, then these things will tell you new.
But as you said, maybe it's about in the end diffeomorphism variance, right? So
The Jacobson, one argument you could make is, I give you any law and then I extend it to be diffeomorphism invariant, and it has to be Einstein's equation. I don't.
I qualify that a bit.
Yeah.
It's more like if you assume the second law, and then you assume the entropy goes like area plus some corrections.
Yes.
You get Einstein's equations plus higher derivative corrections.
Yes, but he.
Diffeomorphism invariant. So it's not just Einstein's equation; it's any diffeomorphism invariant.
but isn't it also
No.
if you have an event horizon? Maybe if you have an event
So
horizon,
that's
any theory with event horizon would not give you something like that.
So there is an equivalency, but I think the logic goes as follows: is that you just assume area law, and you assume the right Chadri equation, right? And that's kinematic. There's no physics there. This implies Einstein's equation. And then you make the area law plus corrections, and this implies Einstein's equation plus corrections.
I think that's how people present it, but I think we're getting off on a tangent. But if you look at the derivation, he starts by proving using the second law and ratio G's equation, but just for a particular slice, and then he extends it over space-time. And when he does that, he's assuming diffeomorphism invariance, and that's a very strong assumption because, in some sense, any diffeomorphism invariant theory will pretty much be Einstein's theory. Einstein's guy with a correction. So that is so he's also making that very strong assumption, which I think is overlooked. But that's a separate point. And I'm not saying that doesn't mean it's maybe a deep result. I just think it's got a lot more assumptions there that maybe people realize.
Yeah, I was just wondering if these other second laws have anything to do with the fact that there are string theories in ADS that are integrable. So there's a lot more going on,
right.
More structure there that maybe is reflected.
Yeah, that's an interesting question. That's an interesting question. I don't know.
And by the way, can I read about this anywhere? Do you have a paper where?
So this stuff this stuff is called are there additional second laws of holographic something or other. So this is with Rob Myers and Alice and Federico. Yeah.
You said that the Jarzynski version of these is probably not interesting in classical limits, but I just remember something about the Jarzynski equation, which is the classical limit is quite non-trivial because it is dominated in that limit by very large fluctuations. So
yes. Well, in a zero temperature limit, it's okay. I wouldn't say in the classical limit, but there are.
Not semi-classical, semi-cold limit.
Yeah, the cold limit, it's very big fluctuations. Yeah. Like I said, so if you believe that Einstein's equations is to do with thermodynamics, it depends whether you believe that. So you might believe that it's just. I guess one way of saying it is, if I have an out of equilibrium black hole, then is the microstructure of the space-time in equilibrium, or is it also out of equilibrium? If it's also out of equilibrium, then you start to believe that things like the Jarzynski equation and these majorization things, which is what lies behind the Jarzynski equation, that these all are important. But if you believe that an out of equilibrium hole has equilibrium, if you believe that space-time is somehow constructed is about equilibrium microscopic degrees of freedom, then you wouldn't believe it. So it's an open, I guess I would say it's just a very open question, and it's certainly worth thinking about. In other words, if you have fluctuations in if you have the fluctuations in your state and in the energy that's going behind, what do those tell you about some fluctuations around the average, the semi-classical Einstein's equations? Maybe. Is that? No, you're looking like I didn't answer your question, or.
I have a conjecture, but it's sufficiently speculative. I'll share it with you.
Okay. I mean, this workshop is the place for.
So I think you've touched on the questions that were on my mind, but just to zoom in on. So you phrased this discussion in ADS-CFT on the boundary about perturbing, but. Do you have anything more to say about what you learn about the black hole when you do that?
I mean, the computation you're actually doing in the bulk, so you're basically doing the path integral and kind of solving for the on-shell action. So you're doing the computation is in the bulk. I can write for you the states and tell you I can't go to these states. So I give you a bunch of states I can't go to.
So what are these things? So what insights do you get from these additional?
I would say there's nothing I could tell you. I can show you a bunch of plots and say, oh, isn't this interesting? But I don't know that I would be able to kind of find the thing that a punchline. You know, what I would like to do is say, oh, the quasi-normal modes are related to the Renyi divergences, and that's the gravitational, there's these, in addition to the area having to increase, the quasi-normal modes have to decrease in this particular way. I would love to be able to say that, but I can't.
So you think you might be on the way? I mean, so as far as you've gone so far,
right.
Like, maybe pointing in that direction? Or,
I think it's giving clues, yeah. So I think we wanted to open the question up and look for smarter people to kind of, you know, look that way.
Starting something.
It's opening the I'd say we've just opened the question, that's it. Okay. And I think you need to understand a bit more about the actual thermodynamics of closed systems, actually, before you can even, I think, before you can address the question. So for people that do resource stage thermodynamics, there's a lot of work to be done there. Which I would be happy to discuss with those people. And for the ADCT point of view, there's a lot of work to be done there. So I think it's just a kind of open question.
So these Hamiltonians are defined by sort of the log of the density matrix, so they're non-local. It's not the same.
Oh, good question. No. So we do it the reverse. Yeah, good question. We do it the reverse way. So of course, if I gave you a state and then constructed the Hamiltonian, what we do is construct a Hamiltonian, and then the state comes from that.
Okay.
So you're just doing a local perturbation on the boundary. You're just adding in some relevant deformation, and so it's still a local. So you can still construct the path integral. I would like to be able to ask. So another good question actually for people is like, can I make this so we can do this construction for a particular class of states where the Hamiltonian is local and corresponds to one of these deformations, turning on a deformation. But a kind of an interesting question is, if I give you an arbitrary state, can I find some path integral or?
Because it's convenient that the partition functions don't appear, right? Because then you're like when you compute the Renyi
right.
entropy, that the partition functions are 1, otherwise they'd be left over in the expression.
Right, but you have to do some renormalization trick as well, though. So, yeah.
Is there a reason why you used your old Renyi divergences and not the sandwich ones?
Because we couldn't compute the other ones. But they'd be the more sensible ones to. In some sense, for different versions of Renyi divergences in the quantum case, they're monotonic for different values of alpha. So you would get different laws depending on which ones you use for different parameters of alpha. Note here, alpha has to be between 0 and 1, so we can't compute for all alpha. So there's lots of questions about these things. What if you want to compute different alphas? What if you want to use sandwich ones, different states, etc. Yeah.
So you use the term additional degrees of freedom.
Okay.
But I think you're sort of resolving. I mean, it's not that you thought the black hole wouldn't have these degrees of freedom before. Is it sort of resolving features of microstates? I mean, are you introducing new degrees of freedom or tracking new degrees of freedom?
Well, okay, so it depends what you believe. So, like, I sometimes have the belief that black holes don't have microstates, but if you,
Fine.
But if you, no, the theme is in context of ADS-CFT. So if you believe ADS-CFT, then the black hole has microstates given by the CFT, and in some sense, you're making a statement about CFT states. And
so you're sort of adding layers of analysis
yes.
to something that was already there when people first wrote down the form of the ADS-CFT picture.
Well, in some sense, you could say, well, if I knew ADS-CFT and I knew the unitary that's happening there, I might have been able to tell you what intermediate states came through. But so this is a way of kind of, but it's a bit more than that, because like thermodynamics is a funny thing. You want to be able to, of course, if I gave you the exact evolution laws, I could tell you exactly what's going to happen. That's not very interesting. It's just too much information. So I want to give you kind of less information, and you want to characterize it in a more crude way, and this does that. But of course, there's but in more detail than the previous one, yes. And but it's in ways which don't depend on the particulars of the evolution. I guess. I just need to know that it thermalizes. I don't need to know anything else about the particulars of the thing. So it's characterizing general things.